Hello everyone. Welcome to my channel Twinkle Teaches. And here is your friend Twinkle. Hope you all are doing good with your studies. As we are discussing all about topology, and here is the next topic in this list, that is Hausdorff or T2 topological space. A better name for Hausdorff topology is given by T2 topological space. So let us see what is Hausdorffness of a topological space. If we are given a set X and there are 2 points from the set X, A and B, such that A is contained in some open set U of X and B is contained in some open set V of X. We have to notice U and V both are open sets of X and A and B are the points belonging to the set X. Then the space X is said to be Hausdorff if U intersection V is empty. Let us understand it with the help of standard definition. A topological space X tau is said to be Hausdorff or T2 space if any two distinct points in X can be separated by disjoint open sets. What does it mean by distinct points? That is, A and B in X with A is not equal to B. Then there exists open set U and V of X such that A is belonging to U and B is belonging to V, and intersection of U and V is empty. A space having this property is known as Hausdorff or T2 space. Two things we have to be very careful with, that is A and B should not be same. Otherwise, the space will not be Hausdorff. Also, we have to notice that U and V should be open subsets, or you can say open sets from the set X. You can choose the sets from tau, because we know that tau is the collection of all open sets. Let us understand it with the help of an example. First of all, we will discuss a very popular example of Hausdorff space, that is lower limit topological space. Lower limit topological space is defined on our towel, which is known as lower limit topology, contains the open subsets of R such that for every point in that open set, the point itself plus some non-zero number R is contained in form of closed open interval. This interval is known as closed open interval, and elements like X, X plus R, where R is a non-zero number, is contained in the open set G, and towel contains this type of elements. Now let us see how it is the Hausdorff space. If in a number line we define points X, Y, 0, and we pick up open sets U as a closed open interval XY, which is containing the point X, and another open set V, which is containing the point Y. But the intersection of U and V is empty. Let us see how. X is contained in U, but X is not contained in V. As you can see here, X is contained in U, but x is not contained in V. Similarly, y is not belonging to u and y is belonging to V. Here you can see y is belonging to V, but y is not belonging to u just because it is closed open interval. This y is not contained in this interval. And y plus 1 is not belonging to any of the set u and v. So x not belongs to u intersection v, y does not belongs to u intersection v, and y plus 1 also not belonging to u intersection v. And there are only 2 or 3 elements which are belonging to the set, and we have checked for all of them. So intersection of u and v is empty. The next example says that every metrizable topological space is Hausdorff. What is metrizable topological space? I have discussed in my previous video and the link is available in the description box. Let we have a set X and A and B are the points from the set X. U and V are the open balls of this metric space XD, and with the property that D of AB, that is distance from the point A and B, is less than R, and the radius of this open ball U is R by 2, and the radius of the open ball V is R by 2. Now we will check whether it follows the Hausdorffness property or not. We will prove it by contradiction method. First, we will suppose that U intersection V is non-empty. U is the open ball with radius R by 2 and V is the open ball with radius R by 2. And A is contained in the open ball U and B is contained in the open ball V. So from triangular inequality of metric space, we know that the distance between the points A and B is always less than or equal to the sum of the distance from A to C and B to C. So what we get is R is less than R by 2 plus R by 2, which is a contradiction that R is less than R, as there is no number which is less than itself. So our assumption that U intersection V is not equal to phi is wrong. Hence, U intersection V is equals to phi and it follows the Hausdorffness property. And any topological space induced from this metric will be a topological space, will be known as metrizable topological space. And every metric space is Hausdorff, so we can say that every metrizable topological space is Hausdorff. Hope you all have got what is Hausdorff or T2 space. So there is a question for you. You have to answer, is the set of all real numbers with the co-countable topology Hausdorff or not? Your options are yes or no. Answer of the question asked in previous video is the option B. So provide me the answer in the comment section. So if you have any suggestions for me, provide me in the comment section. And if you have any queries, contact me at this email ID. If you need PDF version of my notes, provide me your email ID in the comment section. Don't forget to like and share my videos. Please subscribe and press the bell icon so that you will get notified whenever I post a new video. Stay tuned to my channel if you want to get rid of your fear from topology. Enjoy learning. Thanks for watching.